to the course, Changing the World with Chips, Introduction to the Semiconductor. This course introduces you to a semiconductor technology, including a broad range of topics, and also the opportunities within semiconductor industries. Enrolling in this course not only provides you the valuable industry knowledge, but also gives you a lot of opportunity to network with our esteemed speakers. Also, the course serves as a required course for the Semiconductor and Electronics certificate. I am Sophie Tong. I serve as a Semiconductor Co-op Program Manager at Office of Professional Practice. This course is administered by the Office of Professional Practice. Jewel Tord, the Associate Director in the back, and I will serve as instructors from OPP. At the same time, I'm also overseeing the certificate. So please raise your hand if you are already enrolled in the certificate. Yeah, that's a great amount of number. And I hope to see the rest of you in the program soon. Next, within this course, we'll have 4 professors with us. Professor Marknet in the back from ME. Professor Lee, from ECE. Professor Wang, I think she's not here yet, but she'll be here later. And then Professor Wu from IE. Each of them will lead 3 classes featuring industry speakers. As you can see, attendance plays a significant role in this course. Due to the nature of the course, you are expected to come to every single class, as it provides you the best opportunity for engagement. Please be noted that this is a full class with 100 students in this classroom, plus extra 75 students enrolling online. So please value the opportunity to be in this room and to have the networking opportunities with industry speakers. Our TA will provide more details about attendance and extra credit opportunity later. This course schedule starts with a lecture by Mark Armstrong, the Chief Officer of Semiconductor at Purdue. That is what we are doing today. From weeks 2 to 15, we will host industry speakers each week, covering a variety of topics. And then after every class, we will have 30 minutes networking opportunity with the speakers in the same room here. In the end of the course, we'll also have our Vice President for Global Partnerships to come into the class to talk to you about the next steps, and also all the semiconductor-related resources at Purdue. Next, it's our TA. These wonderful TAs will be with you along this course. And then I'll let Hannah and Kaisa to talk about the class logistics.
The assignments mentioned by Sophie, one thing I wanted to highlight was that they're both going to be due on Tuesday to make things simple. For the pre-class assignment, it's going to be the Tuesday before class. So for example, it would have been due yesterday. Nothing this week though. And then post-class assignment would be due the Tuesday the week after, so next Tuesday. And then one thing I wanted to highlight is that we're going to have the optional tours. So I just wanted to give you guys a heads up first, and we'll provide more information later. Thanks.
No worries. We also have attendance policies. So we're going to be passing around an attendance sheet each and every week. So you sign your initials on it and then put down that you're here for attendance. And it's going to be being passed around. In addition, 5 points will be deducted for each missed class, and a penalty will apply if you miss more than 1 class. And you'll also be getting bonus points if you attend all class periods as well. In addition, we'll have extra credit for the Burke Nanotechnology Tour and for full attendance as well. So we also have a survey link. It's on Brightspace. If you guys could fill this out, just scan the QR code and we'll keep going. Basically what this QR code and survey goes to is basically an overview of what you know about microelectronics, what majors are interested in microelectronics, and how you can apply it to it. So it's on Brightspace, so please complete it by today if not done so already. And so nothing is due this week except for the pre-course survey, which is also on Brightspace. And if you're interested in talking to any of our TAs, we'll be holding office hours starting next week. And right after this, we'll be having the co-op call out in the Loeb Playhouse. I'll be talking, so come by. And basically, if you want to learn about co-op opportunities, how to get involved in industry, definitely recommend coming to this event. And so now we have Dr. Lundstrom. Dr. Lundstrom got his bachelor's in electrical and master's in electrical engineering at University of Minnesota and got his PhD at University of Purdue. And now I'd like to introduce Dr. Lundstrom.
All right, thank you. Thank you. So good afternoon, everyone. It's nice to see you here. Nice to see a full room. So my job today is to talk to you about semiconductor technology. Now, I actually don't know how long I have. How long is the class?
50 minutes. 50. It goes until 5:20. You have around like 40.
40 minutes? All right, we can do it. I mean, there's a lot to talk about. So what is semiconductor technology? It's absolutely fundamental, foundational to everything we do. The modern world would not be possible without it. There are chips inside everything. So it's critical to the defense of our nation, to our economic security, to addressing every challenge we face, whether it's climate or energy or health or transportation, whatever we do. There are career opportunities in this field, whatever your degree is. And even if you don't end up working in this field, you'll end up depending on semiconductor technology. So it's good to know something about what this is all about. So in this course, every week, a speaker will come in from a different part of this industry and talk about their role in the industry, what they do, how it makes the world a better place, what career opportunities there are for you, whatever your degree, whatever you're majoring in. And my goal today is to try to present a big picture. What is this field all about? So that when individual speakers come in, you know what piece of the industry they're talking about and how it fits in with the overall industry. So I have a lot of ground to cover, so I should probably jump into things here. Whoops. Let me go in the right direction. All right, so semiconductor technology is a high priority of the nation right now. So this is the CHIPS Act that was signed a little over a year and a half ago. So that's President Biden. Right behind him is the senator from Indiana, Senator Todd Young, who was co-author of the CHIPS Act in the Senate. So this is a high priority of the nation because it is so important. Other countries have CHIPS Act too. There's a CHIPS Act in India, there's a CHIPS Act in Europe, there's a CHIPS equivalent of a CHIPS Act in Japan and Taiwan and Korea. It's such an important technology and everybody understands it and everybody is investing an awful lot in it. So this is being described as a once-in-a-generation investment. There's something like $300 billion of investments that have been made since the CHIPS Act was announced. This is going to be an industry that, this is actually my 50th year. I've been working on this field since my first job out of college, but it's never been more exciting. And for the next 2-3 decades, it's going to be a growing industry in the US. So it's really a perfect time to get into this field. So what are the objectives of the CHIPS Act? So one is to bring more manufacturing, more semiconductor manufacturing back to the US. Over the years, we've outsourced more and more of that. And then we had COVID, and we found out that, whoops, that's really dangerous. You couldn't get an automobile because they couldn't get chips for the automobiles, and who knew there were 3,000 chips in every automobile? So it suddenly was a wake-up call, and people understood how important this technology was. So a lot of it has to do with bringing more manufacturing back. The US is really strong in the design of chips, and we're really strong in the sophisticated tools that are inside these factories that are involved in the manufacturing of chips. And we want to bolster our strengths in those areas and basically regain our lead. So over the years, the leading edge chips, the most sophisticated chips, the ones in your highest end cell phones, the ones that are doing all the AI today, we've lost our lead in the leading edge chips, and one of the goals is to regain that. Turns out 97% of the leading edge semiconductors now come from one company in one country, and that's Taiwan. That's kind of dangerous to be so reliant on one place. It's an earthquake-prone zone, so think what might happen. And the other is to accelerate the pace of innovation. The way the US has traditionally stayed ahead is by inventing and outpacing others. And the pace of innovation continues to be very rapid, but we want to speed it up even more. So those are the objectives. And my goal today is to tell you a little bit about this and what you're going to be hearing about in the course. And you'll have many career opportunities, but among the opportunities that you have, you should think about an opportunity in this industry because it's really important, it's really exciting, and it's going to be growing for years and years. So microelectronics, you sometimes hear the term microelectronics. So that's the design of these chips, which we'll talk about in a minute. The chips are made on materials called semiconductors. So we sometimes call it semiconductors or microelectronics, it's the same thing. The fundamental building block of electronic systems is a device called the transistor, and we'll talk about that. They have gotten incredibly small. Their critical dimensions now are measured in nanometers. And a leading edge chip might contain 100 billion on a small, 1 inch by 1 inch chip. And it's interconnected by a lot of wire to interconnect 100 billion transistors. That's actually 60 miles or so of wire on a leading edge chip. So, a little bit of background and basic tutorial. What is a semiconductor? So I think most of us know what a metal is, and metals tend to conduct electricity really well. We know what an insulator is, things like glass that don't conduct electricity very well. And then there's a semiconductor, which sort of conducts electricity. It's not as good as a metal. It's not as insulating as an insulator. So what's the big deal about semiconductors? The big deal is that by inserting small numbers of other atoms in a semiconductor, you can dramatically change its electrical characteristics. You can make it more metallic, or you can make it more insulating, and that's the way we make transistors and electronic devices. So it's that property that makes them so important. So what I'd like to do is to tell you just a little bit of fundamentals about this field. And then you're also at an interesting time because things are changing in this field right now. We're not just continuing what we've done for the previous 50 or 60 years. We're really at an inflection point and things are changing. I'll talk a little bit about that. And then a little bit about the industry and the career opportunities that will be available for you. All right, I won't go, semiconductors are in everything. The flat panel displays you have are really semiconductor devices. Your cell phones are chock full of chips. Laptops, data centers for your cloud computing. Automobiles include thousands of chips, and electric vehicles include even more. The solar cells, when you drive by outside in the country and you see these solar arrays, those are semiconductor devices. Appliances are full of chips now. So more and more chips in more and more things, and they're more and more important for everything. Now, what's driving everything really aggressively right now is artificial intelligence. It has an insatiable appetite for computing and for memory, and this is what the industry is trying to keep up with. So if you look at this, this is a plot that shows the increase in computing power versus time since 1952. And it's been increasing rapidly. It's been doubling every 2 years. But now with the onset of artificial intelligence, in the last decade or so, the need for computing is doubling every 6 months. And this is what the electronics industry is trying to keep up with. That's what makes it exciting. Okay, I mentioned this before. Whatever challenges we face will require more computing, more data, more communication, and semiconductor technology is the foundation for all of that. So I think every country has realized now that you need to be strong in semiconductor technology if you want to control your destiny. So it's a really critical technology. All right, so a little bit more. So let me go back in history. So this is a light bulb. And it's sort of a light bulb. So back when Thomas Edison was working on inventing his light bulb, you have a filament in this vacuum enclosure, and he noticed that the bulb got dark over time. And he thought, well, something is coming off of the filament, but he didn't know what that was, and he had more important things to do, so he didn't get to the bottom of it. Well, a physicist in England, J.J. Thomson, spent a little more time to get to the bottom of it and figure out what is it that is coming off of this hot filament, that's lighting up the light bulb. And it turned out what's coming off are electrons. And he received the Nobel Prize for discovering electrons, basically. Whoops. Very quickly after that, another British physicist realized that, hey, I could make an electronic device that does something useful with this. And J.J. Fleming, I forget what his first name was, invented a device called a diode, based on the vacuum tube, which conducts electricity in one direction but not in the other. And then a few years later, in the US, Lee DeForest invented a triode, and that's what you're seeing here. So this is an amplifying device. So there's a filament, you run electricity through it, it heats up, just like a light bulb. There is a plate, so electrons come off. There is a plate. Whoops. I'll get the hang of this. There is a plate that you put a positive voltage on. Positive voltage attracts the negatively charged electrons and a current flows. And in between the plate and the filament, there is a grid. And if you put a negative voltage on it, it repels the electrons and pushes them back so they don't get to the plate. If you put a positive voltage on, it helps them get to the plate. So you can control the flow of current from the filament to the plate with this grid. And that's the way you amplify small signals. You put them on the grid, and it amplifies the current that flows from the filament to the plate. So that was a really big deal because it was a useful electronic device. And at this time in history, this had a huge impact. So it ushered in what's called the golden age of radio. Suddenly you had entertainment, you had presidents who could give fireside chats, and the whole nation could hear at the same time. It was a really big deal. It never happened before. People started building computers with vacuum tubes too. So this is the first computer. I think it was built at the University of Pennsylvania near the end of World War II, built with vacuum tubes. It had over 17,000 vacuum tubes. So lighting up all these vacuum tubes is like lighting up 17,000 incandescent lights at the same time. Consumed a lot of power, 150 kilowatts. Big machine that filled up a whole room, weighed a lot. And I forget now, it has a fraction of the computing power that we all carry around with us right now. And these light bulbs burn out, these vacuum tubes burn out. They're not very reliable electronic devices, and that's a problem. So one of these people had the full-time job of every time a vacuum tube burned out to run back and replace it as quickly as possible so you could continue computing. So this was a big challenge because it wasn't a very reliable electronic device. And everyone knew that, well, there must be something better. Well, during World War II, there was a lot of research on semiconductor technology to develop things like detectors for radar and devices like that. There was a lot of this pioneering work was done right here at Purdue in the physics department, where in the physics department at Purdue, they learned how to grow a semiconductor called germanium, to grow it in crystalline form, to dope it so that it changed its electrical properties, to measure the characteristics. There had been so much advanced in the basic understanding and technology of semiconductors during the war to do things like radar detectors, that it was realized at Bell Labs that the time is ripe. We could build an electronic device out of semiconductors. And that device was demonstrated in 1947 at Bell Labs. Big press, well, not a big, there was a press release in the New York Times on like page 10. Nobody paid any attention to it because, you look at this device, this is a model, this looks like a bent paper clip. Down here is the semiconductor slab. They learned, actually at Bell Labs, they learned how to grow germanium crystals from the people at Purdue. But it would be hard to predict, looking at this device, that it would change everything. But it's been called the most important invention of the 20th century. It had a big impact. And you know, you can go online and you can find some videos that, I mean, it's a really fascinating story. There's some interesting personalities involved in this, and it's fun to watch. Okay, so it actually wasn't a particularly good device. It couldn't replace vacuum tubes in a lot of applications, but it could do some things that vacuum tubes couldn't do. So for example, you could operate it with a battery and you could carry it around. So it was this, you know, people very soon, they began building hearing aids out of transistors. You know, you couldn't do that with vacuum tubes. And this is the first transistorized radio. Built in 1954. It was actually manufactured in Indianapolis. And I understand that the audio quality was not that great, so it wasn't a big hit in the marketplace. But just a few years later, there was a better transistor radio made by a company in Japan called Sony. It was a brand new company at that time. It was a 6-transistor radio, and it had good quality. This ushered in consumer electronics. You know, you could carry the radio around with it. I'm old enough, I can remember. You know, I was 6 years old at that time, and suddenly kids had transistor radios they could carry around. It had 6 transistors in it, and then your friend down the block would get a 12-transistor radio, which of course was much better because it had more transistors. And then you had to get, you know, an 18-transistor radio. We very quickly began to measure the performance of an electronic system by the number of transistors that were in it. So that was a big hit. He called it a shirt pocket radio because it could fit in your shirt pocket. Actually, it didn't fit in the shirt pocket. He had custom shirts made for his salesmen that had a little bit larger shirt pocket, so when they went around they could market their shirt pocket radios, but it was a huge hit and got things started. Now, so that was a very big deal. Some people say that was the most important invention of the 20th century, but Isaac Asimov, do you know this name? You know, no longer alive, famous science fiction writer. So he said that something else was the most important moment since humankind emerged as a life form, and it wasn't the transistor. What could it possibly be? I tell people it's almost impossible to overstate the importance of this technology, but Asimov came close, right? So what was he talking about? He was talking about what this fellow, Gene Horney, invented. And what he invented was a process to manufacture transistors better. All right, what's the big deal about that? Well, the big deal was he was doing that at a company called Fairchild, which was the first Fairchild Semiconductor, which is in Silicon Valley, which is actually the second really semiconductor company in Silicon Valley. And his boss, Robert Noyce, realized that, hey, I could not only build a transistor on one piece of silicon with this new manufacturing process, I could put 2 transistors or 4 transistors on that same piece of silicon. I could wire them all up at the same time with this manufacturing process. So that was called the integrated circuit. Everything is integrated into one piece of silicon. That's a chip. And that was done at the first time, demonstrated in 1960 at Fairchild. And that was a very big deal. And it used this planar process that his colleague at Fairchild had invented, Gene Horney. And it also took advantage of something called the John Atala's surface passivation process. Now, who is John Atala? I'll come to that in the next slide. So this was a very big deal, and people could begin to make chips. It was a small niche market for a long time. You know, most of the electronics was vacuum tube electronics for a long time. In the first half of the 1960s, most of the chip market, most of the chips were purchased by NASA for the space program. You know, and this is a logical NOR chip. So I think it's got 2 transistors on it. And it was used in an onboard computer for the Apollo spacecraft. You know, people will say that the major reason that the US won the space race is because we had onboard computers and the Russians didn't. So this was a driver for semiconductor technology in the early 1960s. And now the transistor that is used today is not the transistor that was discovered at Bell Labs and that was used in the first chips. It's a different transistor. It's called the MOSFET, metal oxide semiconductor field effect transistor. This is a cross-sectional slash of it. The first transistor was made in Bell Labs in 1947. They were trying to make this transistor but couldn't make it work. In 1959, other people at Bell Labs figured out finally how to make it work. So it's a piece of silicon. It has terminals here that are very descriptive. There is a source region that has been doped with other elements, so it has an excess of electrons. And there is a drain region that is also doped. All right. And you attach wires to the source and the drain. And then there's a gap between the source and the drain, so the electrons can't get across it. There is a gate in between the source and the drain. And if you apply the proper voltages, let's say I apply no volts to the source, I apply some voltage to the gate, and I apply a positive voltage to the drain. The positive voltage on the drain wants to attract the electrons and pull them out of the source and let them flow out the wire, but they can't get across that gap unless you apply a voltage that's big enough, and then you turn the transistor on. So you could do digital logic. The transistor is either off or it's on. Okay. So that's the device, and that device was invented by John Mohammed Atalla, who was a PhD from Purdue University, did his PhD in 1949, mechanical engineer. He went to work at Bell Labs and became a terrific semiconductor physicist and surface scientist, and he discovered that if you did things properly, you know, the surface of a semiconductor wafer is highly defective because it doesn't have other silicon atoms surrounding it to tie up all the bonds. So it has lots of defects that don't permit charge to flow. He discovered that if you grow a silicon dioxide, basically quartz, glass layer on top of it properly, you can electrically neutralize all of those defects so that they don't impede the flow of charge. That was a really big deal. And then he realized that, hey, I can make the transistor that we were trying to make in the first place. And he realized very quickly also that this transistor is ideally suited for integrated circuit chips. And he realized that in 1959 or 60. And this is the transistor, you know, when we say there's 100 billion transistors on a chip, it's this kind of transistor. These are the transistors that we're manufacturing. Okay, so I'm trying to give you, some understanding of some concepts that you'll hear throughout the semester as different people come in. This planar process is a really big deal. So, and you'll hear about it from various companies that do various things in this. How does it work? Well, I begin with a wafer. I'm calling it P-type here, and it means it's been doped so that it has positive charge carriers. Okay. And we either deposit or we could oxidize it and grow a thin layer of something on the wafer. Okay. And then we coat this material with something called a resist. This is a photosensitive material. So you probably all don't remember photographic film, how you would take a picture and have to develop it. Well, it's sort of like a photographic film. It's a material that is sensitive to light. And now, we want to expose a pattern so that we can make our transistor, our source and drain regions. So we have a mask, which is going to let light through in the source and drain regions, but not elsewhere. And then we have an illumination source, and we turn it on. We illuminate this. The light goes down. There's a chemical reaction. There's the physical change that occurs in the resist. Once that resist is changed by exposure to the light, we can develop it, put it in a chemical that dissolves away the resist where it has been exposed to light. Now we've transferred the pattern from the mask to the resist. Then we expose the wafer to a chemical etch, which selectively etches the film on top, but not the silicon. Now we've transferred the pattern to the film, and now the resist has done its job, so we strip the resist off. So it's that process that's done over and over and over again, maybe hundreds of times in a manufacturing process for semiconductor devices. So we have our wafer. We've now patterned the layer on top of it. Maybe we want to dope the semiconductor by introducing some other elements in it that change its electrical properties. So one way to do that, arsenic is a dopant. We put it in a machine that's called an ion implanter that ionizes it so it has a positive charge, has a huge voltage difference that accelerates that positive charge, and we shoot them into the silicon wafer. Okay. They can go through the layer on top where there are holes, and now we've selectively doped the silicon, and we've produced this source and drain region. Okay. All right, so we have our wafer doped. We have to put metal contacts to it. We deposit metal. Of course, it goes up and down and over the contour, so it's not flat. So we do something called chemical mechanical polishing to make it flat, because the next processes are going to require a flat wafer. So now we've got metal, but everything is shorted together. So now we need to pattern the metal. So we go through the same process again. We put the resist on. We have a pattern. We expose it. We transfer the pattern to the resist. We put it in a chemical that etches the metal, but not the glass layer underneath it. And then we strip the resist off. Boom. And we've got a transistor. Not a great transistor, just, but it would work, And this is the process that this fellow Gene Horney invented in 1959, and we use a very sophisticated process today. This is what Isaac Asimov called really, really important. So that's what's made integrated circuits possible, and it's also this idea that work that came from one of our own alumni who learned how you can passivate these surfaces so that they are not electrically defective, but they allow charge to flow from the source to the drain. All right, now I want to point out, there's all kinds of interesting problems. Everywhere you look, there's an interesting technical challenge. Now you may know, have you done this in physics? If you shine light through a little pinhole, it spreads out, right? It diffracts. Now, since you're trying to make patterns smaller and smaller and smaller so that you can put more and more and more transistors on the chip, your holes, the patterns are getting smaller and smaller every year. Well, the light diffracts and it spreads out, and the pattern that you transfer is bigger than the one you want. So diffraction limits how small you can make patterns on the wafer. Okay. That smallest pattern is usually the gap between the source and the drain, and that's called a critical dimension. Okay. So it's important what wavelength you use when you're exposing the light, because the critical dimension is actually proportional to the wavelength. Oh, I'm missing it should be 0.25, this constant K, and that one should be a lambda, a wavelength, the wavelength of the light. Basically, the shorter the wavelength, the less diffraction there is. So over the years, people have they started using optical light, then they started using ultraviolet, then they started using deep ultraviolet. Eventually they got to X-rays, shorter and shorter and shorter wavelengths of light. So for many years, it was 193 nanometer wavelength. Today, the most sophisticated tools that are used to expose these patterns are something called an extreme ultraviolet lithography system. There's only one company in the world that can manufacture this tool. This is one of the tools inside a chip manufacturing factory. These tools, they're incredibly sophisticated. This particular tool costs $250 million each. My first job out of college was working on this technology. The corresponding tool cost $25,000. Now it costs $250 million. So things have gotten more and more sophisticated and more expensive, but we're manufacturing more and more chips, more and more transistors on the chips all the time. So the cost per transistor has actually dropped dramatically. So they're doing a great business. They can't make these fast enough. But there are really only 3 companies in the world that can afford to be in this game now, because building a chip factory costs about $20 billion. It gets more all the time. The next generation of this tool is going to cost even more. But that's what it takes to continue to push this technology forward. I believe that your next speaker in this series is a speaker from ASML. So you'll know what they're talking about. Okay, so it's all about silicon wafers and chips. These days, most of the manufacturing, or at least the high volume manufacturing, is done on silicon wafers. So these are single crystal pieces of silicon, probably the most pure material that human beings manufacture right now, grown into a big bowl and then sliced up into wafers and polished. And if you look carefully, you can see there's a bunch of rectangles on there. Each one of those rectangles is a chip, which will eventually be cut up and diced and inserted into a package like this with a lot of wires on so you can connect it to the rest of the circuit. Okay, so bunch of individual chips. The largest the largest CPU or graphical processing unit chips will be about 2 centimeters by 2 centimeters, just a little less than an inch by an inch, and can have lots of transistors on it. If you do a cross section, if you do a slice and look at a cross section to see what's here, what you'll see is way down at the bottom is a silicon wafer. And then if you look very carefully, you can see the transistor here. Here's the source, here's the drain, here's the gate. But it takes an awful lot of wire to wire up billions of transistors. So there's level upon level upon level of metal above that, crisscrossing and wiring up everything that needs to be wired up. Okay, so, all right, so Moore's Law, is that a term that people have used? Okay. Yeah, what is Moore's Law? Well, basically, it's been going since 1960. And in 1965, Gordon Moore, who was working at Fairchild Semiconductor at that time, and later co-founded Intel, noticed that every year the number of transistors per chip doubled. And he predicted that this will probably continue for at least 10 years. And what did it? It continued for 50 years. Nobody could have believed it. It slowed down a little bit. It began to double every 2 years for a long, long time. But that's exponential growth. Every 2 years you double. Every 2 years you double. And that's how we've gotten from where we started to where we are today. Now, what is NMOS2? That's the technology I was working on in my first job out of college. And we called that a 5 micrometer process. That was the gap between the source and the drain. Today we would measure that in nanometers. A nanometer is 1,000 times smaller than a micrometer. So today that would be called a 5,000 nanometer process. And it was really, really, really hard to make that work. That was leading edge technology at the time. But today's technology is 5 nanometers or maybe 3 nanometers. So the gap is 1,000 times smaller. The area of the transistor is 1,000,000 times smaller. So we can put more like tens of billions of transistors on a chip these days. Okay, so this has sort of been, it's not a physical law, well, it's called Moore's Law. It was just an observation. And it became a self-fulfilling prophecy, because no company could afford not to double the number of transistors on their chip in 2 years, because they knew if they weren't smart enough to do it, their competitors would figure out how to do it, and they would be out of business. So for year after year after year, it was like a freight train going down the tracks. You just figured out how to make transistors smaller and smaller and smaller and smaller, and things got better and better and better and better. And it's not easy. Lots of students graduated and went out. Many times the end of Moore's Law was predicted. Bright students went out there and figured out, okay, it's not done yet. We can figure out how to keep it going. You look about the year, here's 100 million transistors per chip. Once you sort of reach that threshold, amazing things could be done. So I think about that time, about 2007, the iPhone was introduced. Suddenly, a lot of things that we just think of commonplace today were possible, because you had so much electronics available on these chips. Okay, all right, this is an Apple M2. It's got 67 billion transistors, and it's just, unbelievably complicated. Manufactured by this one company in Taiwan, TSMC, the largest manufacturer of chips today. And we just continue to progress. This is called a system on chip. That's been the focus. Put an entire electronic system, put everything onto one chip. That's what the focus has been. Okay, so, and it's interesting. So it's named after Gordon Moore. This is quite a few years ago now. In 2019, he pointed this out. At that time, there were 5 billion transistors on a chip, and we thought that was almost unbelievable. And he pointed out no other technology has improved at the rate that this technology has improved at. So if automobiles had improved at this rate, you'd get 100,000 miles per gallon. And if the cost of the technology had declined the way the cost of semiconductor technology has declined, what does he say? A Rolls Royce would cost less than it would cost you to park it in the parking garage. So that's what electronics has been all about. Increasing performance and lowering costs over a long period of time. Okay, but things are changing, and I think that's what actually makes it exciting and interesting. There's a lot of debate about the end of Moore's law. Is it here? Some people say yes, some people say no. I think what you can't deny is it has slowed down recently. It takes more like 4 years now to double the number of transistors per chip, but it will continue to go probably for a decade, maybe for 2 decades. But we need to find other ways to advance the performance of electronic systems because things like artificial intelligence just can't get enough computing. How do we keep up with that? Well, we have these silicon wafers, and we have chips. We dice up the chips, we package them in packages, and this is a very sort of a low-tech thing, the actual packaging of chips. Dicing them up and putting them in packages. It's labor intensive. The US has outsourced 97% of this industry. It's just not cost effective for us to do this. But there's something else that's on the horizon, and this is what people see as the way that we're going to continue to advance the performance of electronics for a long time in the future. And this is called an advanced package, which is much more sophisticated than this one, has much finer lines, done in factories that are closer to the chip manufacturing factories in terms of the technology they use. And the idea is that you can put multiple chips into that package. Now, why is that important? Because if your printed circuit board or whatever on your laptop or in your cell phone contains a number of different separate chips in separate packages, every time you send a signal from one chip to another, there's delays that are introduced. And it costs you power to send it from one chip to another. So having separate chips has all of these disadvantages. But we can't make chips much bigger than we're making them now, and we can't put many more transistors on the chips than we're making now. But what we can do is we can package them together in a sophisticated, advanced package where we can put them in intimate contact. So it's almost as though we've made one very large chip out of some multiple chips. And we can even mix and match technologies. We can put memory chips and logic chips together. Those are two completely different manufacturing processes, so you can't manufacture them on the same chip very well. We can put older technologies with newer technologies when we don't need the newest for everything. So there's a lot of advantages to that, and people see a lot of hope in that. And we're making a transition. For the last 50 years, it's been all about putting the entire system on the chip, or as much as you can. The future is going to be about putting the system in an advanced package, and we'll continue to progress that way. So this is what an advanced package might look like. You look at a cross-section inside one of those packages. There's a company, SK Hynix, which is really a leader in this field now. Many other companies are chasing them. And what they do is, NVIDIA is probably the leader in the multi-core GPUs that power artificial intelligence these days. But these GPUs can't get enough data fast enough. What SK Hynix does is they stack memory chips vertically. You might have as many as 16 chips stacked vertically so that you get lots of memory. And then they are connected to the logic chip through something called a silicon interposer, which has many fine lines and can connect the memory to the GPU so data can go back and forth at a very high rate. So this is what's inside an advanced package, and we'll be seeing more and more of that in the future. So if you look at Moore's law, the question is, how much longer can this work? Can this happen? It's usually plotted as number of chips per, number of transistors per chip versus time on a log plot like this. And we'll probably continue to do this for the next 10, 20, 30 years, but we'll be plotting the number of transistors per package, because that will be the thing that is more relevant. And we'll end up with trillions of transistors per package, probably, and incredibly complicated, powerful chips. All right, now this is an area actually of particular strength at Purdue, this area of advanced packaging. We have a lot of faculty that are working in this area. We have a new institute that we just launched last October to focus on this. We're thinking about, some of you are aware of the STARS summer program that we offer. We're thinking about adding an advanced packaging track to that summer program because it's so important. And companies are finding they can't find many students who have much understanding and experience with advanced packaging because it's a relatively new technology. So you might have an opportunity to learn more about that in the STARS program. All right, let me talk a little bit about industry. I only have a few minutes left, but I want to give you a little sense of what this industry is like. One way to think about this is there are different kinds of companies. There are companies that are called fabless companies. They design chips. They do not manufacture chips. There are companies that are called foundries. They just manufacture chips that other people have designed. And there are other companies called outsourced assembly and test factories that package them and test them. Okay. Well, there are a whole bunch of other companies. There are actually thousands of different companies in the semiconductor ecosystem or supply chain. There's a set of companies that do this fabless design, and you've probably heard from some of them. NVIDIA is powerful in the design of AI chips. They don't manufacture the chips, they design chips. Other companies like MediaTek is located right here on campus. They've opened they're the fourth largest fabless design company in the world, and they've opened their first Midwest office here on the Purdue campus. But other companies that you don't even think of as semiconductor companies are doing this. Apple, a number of years ago, began designing its own chips because companies are realizing that more and more what differentiates their products from their competitors' products are the chips. And if you're using commodity chips that anyone can buy, it's harder to differentiate yourself. Tesla designs its own chips. Every automobile manufacturer has announced that they'll be designing their own chips in the future. So a lot of companies that you don't think of as semiconductor companies are involved in this. And then there's a whole different set of companies. The electronic design automation tools that are used to design a $100 billion transistor chip are incredibly sophisticated. And there are companies that just develop and support this software. And I'm sure you'll be hearing from some of these companies like Synopsys and Cadence later on in the semester as well. And then foundries. So TSMC is the largest foundry. Intel is building a very big factory in Ohio. This will be a foundry, Global Foundries. UMC is in Singapore. So there are a set of companies that just manufacture the chips that other people have designed. And there's a whole different set of companies that support these manufacturing facilities. So there's a set of companies that provide the wafers and that provide the chemicals and the materials that are used in the chip manufacturing process. There are a set of companies, and you'll be hearing from some of these, that produce the tools that are used inside the factory to manufacture the chips. So a wide variety of companies. And then there are these outsourced OSATs, and this is the part of the industry that is very labor intensive and low profit margins, most of which has been outsourced. But there's a plan in this industry to bring more of the packaging industry back, not the low-end packaging, but the very sophisticated high-end packaging, the advanced packaging. There are also companies that are called integrated device manufacturers. And they design chips, they manufacture their own chips, and they might package their own chips. And some of those that you see here, some companies are both. Intel is an integrated design manufacturer, but they're creating a new foundry in Ohio, so they'll be doing both. All right, now I better wrap up. This is some data that some companies provided to us about a year or so ago about their new college hiring data. We asked, what kinds of people do you hire? And I want to show this, even though the data is a little incomplete, so you can get a sense. Now, if you look at the fabless companies, the companies that design chips, they very heavily rely on electrical and computer engineers and computer scientists to do the chip design. But if you look at the foundries, there are fewer electrical engineers. There are many more chemical engineering, chemists, materials engineers, industrial engineers, physicists. And if you look at the tool manufacturers, that's a different profile. Lots of chemical engineers, mechanical engineers, materials engineers, industrial engineers. So different parts of the semiconductor supply chain have different needs in terms of the amount of talent. I don't have the material suppliers up here. That would be probably high chemical engineering, materials engineering people. So whatever your degree is, there is undoubtedly an exciting career opportunity for you here. I'll point out that the engineering jobs in this industry are about 50-50 between BS degrees and graduate degrees. Slightly more than half of the positions actually are graduate degrees. Masters are in particularly heavy demand, but also PhDs. All right, so let me wrap up. So, we're really beginning a new era in semiconductor technology. I'm jealous, you guys are right here at the right time. Things are getting exciting and are going to be exciting for a long time because this technology is so critical and so important to the nation. Electronics is going to be getting more and more powerful, but also more and more differentiated because people are looking at, how can I use semiconductor technology in a much different set of applications and challenges, digital agriculture and all kinds of different things. So the pace of innovation will be very exciting. It'll get faster and faster, but it will be more and more diverse. We won't have this predictable roadmap that I had my entire career, where, all right, in 2 years, we have to put twice as many transistors on a chip. There will be much more variety that will have to be done. We won't have we won't have a Moore's law to guide us. That's going to make it exciting and interesting. Universities have an important role to play. When the companies come to us now, and we have more of them coming to us than ever before. I've been here at Purdue for over 40 years. There are more companies coming here looking for semiconductor talent than I've ever seen. They're building factories and expanding their offices and things. Their number one challenge, they say, is where are we going to get the people to do this work? So you're in a good position at a good time. So going to be lots of exciting career opportunities for you. Future is bright. So, we have a web page. You can find more information there. And I hope throughout the duration of this semester we can give you more information on the summer program, more on how you might earn a certificate or a concentration and see whether this is a field that you really want to dive into. We have vertically integrated projects, student teams where you can design a chip or you can work on chip manufacturing. We're going to probably launching one on advanced packaging. So there'll be lots of opportunities there. So I think I've gone a little bit over, but I covered everything I wanted to cover. I hope you find it as exciting as I do. I think you're in for a real treat this summer.
Thank you, Mark. And then that's all for the class today. There are a lot of speakers coming from the company that Mark mentioned today, so looking forward to all the speakers' lecture in the future.